You ever wonder if our universe is just some kind of cosmic accident? Like, if the laws of physics are just a random set of rules that happen to work out? Well, there's a bold new idea called modal theory that says no way. It claims our universe is the only possible one that could exist. Now, that's a huge claim, so let's dive in with a healthy dose of skepticism and see if the case it makes really holds up.
At the very heart of this whole thing is one really radical question. What if all the numbers that define our reality, the speed of light, the mass of an electron, aren't arbitrary at all? What if they're actually the only values they could ever be? All because they're cooked up from a single, much deeper principle. So to really get why an idea this wild is even on the table, you have to look at our best theory right now, the standard model of particle physics. And don't get me wrong, it works incredibly well, but it's less like one elegant equation and more like a super complex machine with this whole control panel full of mysterious dials, and each one is tuned to a value that's just perfect, too perfect maybe. And the question that keeps physicists up at night is who or what set those dials?
And yeah, as you can see, there are a lot of dials. We're talking more than 19 of these free parameters. And these are numbers the standard model just can't predict. We literally have to go out, do the experiments, measure them, and then plug the numbers into the equations by hand. They control everything from how heavy a particle is to how strong a force is. The theory works, sure, but it gives us zero reason why the numbers are what they are. It just feels, profoundly incomplete.
Okay, I know, that's a mouthful. But what modal theory is trying to say here is, let's flip the whole problem upside down. Instead of a bunch of local rules that just happen to work everywhere, what if there's one single, universe-spanning rule of consistency? The idea is that everything we see, every law, every particle, every one of those constants, is just the universe settling on the only configuration that is completely, totally self-consistent.
So how does the theory propose to pull this off? Well, here's the core claim. It tries to replace all 19 plus of those mysterious dials with a single, foundational geometric rule. It argues that our universe isn't just one lucky shot out of a bazillion possibilities, but the one and only logical outcome of a ridiculously simple geometric idea.
The theory's foundation is almost deceptive in its simplicity. It starts with just two basic fields called scalar fields that exist everywhere in space. You can think of a scalar field like a temperature map of the universe, just a background value at every single point. And in this theory, the way these two fields, phi1 and phi2, interact with each other, well, that's what generates everything else.
Now, you're probably thinking, wait a minute, how can two simple fields create all this complexity? The key, the theory claims, is something called a phase lock. Think about a slightly unbalanced wheel. It doesn't matter how you spin it, right? When it finally stops, the heaviest point is always going to settle at the bottom. It finds its stable spot. The theory says the universe did the exact same thing. These two fields interacted and just dynamically settled or locked into one single, stable angle relative to each other, everywhere.
So what is this cosmic angle, this magic number? It's not something simple you'd guess like 90 or 180 degrees. No, the theory claims the entire universe is built from the phase difference between these two fields locking in at one very specific, kind of weird number, 255 degrees. If this is right, that one number is the blueprint for literally everything.
Okay, but let's be real for a second. How can one number, one angle, possibly explain the mass of a top quark, the strength of electromagnetism, and the whole cosmic shebang? I mean, that is an extraordinary claim, and it's going to need some extraordinary evidence. This is the part where the theory has to, show us the receipts.
Let's take one of the most famous numbers in physics, the fine structure constant. It controls how light and matter talk to each other, and its value is roughly 1 over 137. So the theory claims it can derive this from scratch. It starts with an assumed geometric shape for spacetime, a Z3 orbifold, for the nerds out there, which gives a base value of 126. Then that crucial 255-degree phase lock comes in, creates a bias, and adds a correction of about 11. And the final result? 137.036. That matches what we measure in labs with just stunning precision. And this isn't a guess, it's a step-by-step calculation.
And it's not a one-hit wonder either. The theory claims to get a whole bunch of these constants from that exact same angle. I mean, just look at this. The electron mass is spot on, the top quark mass is incredibly close, even some of the really obscure values, like the angles that tell us how quarks decay, they seem to just fall right out of the geometry. The whole idea is that all those different dials on the machine are actually connected to one master dial, and it's set to 255 degrees.
Okay, so if the fundamental constants are really set in stone by some universal geometry, then that has to have a ripple effect, right? Everything built on top of those constants has to be constrained by that same geometry. And this idea totally reframes fields we thought we had figured out, like chemistry.
So we normally think of chemistry as just, electromagnetism and quantum rules doing their thing. But modal theory says, hold on a minute. It suggests the vacuum of space itself acts like a geometric filter, almost like a template. Molecules aren't stable just because the forces say so. They're stable because their actual physical shape is compatible with the geometry of space-time. An unstable molecule in this picture is one whose shape would create a wrinkle in that geometry, and the universe just won't allow that.
This right here, this really maps out the entire domino effect the theory is claiming. It all starts at the top, with that phase locking in at 255 degrees. The theory says this directly causes that tiny bit of extra matter over antimatter that allowed us to exist. That imbalance, in turn, sets the mass for all the particles we see. And finally, those masses correctly predict how many light elements got cooked up in the Big Bang. It's a single, unbroken chain of cause and effect, and it all starts from one angle.
So far, this all sounds like an incredibly elegant, neat, and tidy story. But in science, elegance isn't enough. A beautiful theory that you can't prove wrong isn't science. It's just a nice story. So the absolute most important question any skeptic can ask is this: how could we test it? How could we break it?
Because I know what you're thinking. Sure, the predictions match data we already have, but that could just be a clever trick, fitting the theory to the facts after the fact. And you're right to be skeptical. To be truly convincing, a theory has to stick its neck out. It has to make new predictions about things we haven't seen yet. So, does model theory do that? Does it offer up any real testable claims?
The answer is a huge yes, and the predictions are surprisingly concrete. The theory predicts we could actually build a device that could produce a tiny but measurable physical push in a lab. It predicts that gravitational waves from colliding black holes should have these little specific distortions that our next-gen observatories might be able to see. It even predicts a precise lifetime for the neutron that could solve a really nagging puzzle in physics. See, these aren't vague ideas. They're actual experiments with clear yes or no answers. If we look for these things and they aren't there, the theory is just plain wrong. End of story.
And that really brings us to the final and most provocative question of all. Is our universe just some cosmic accident, a lucky draw from an infinite lottery of possibilities? Or is it something way more profound, the only possible universe? The single, inevitable, logical outcome of one simple geometric rule. The answer, whatever it is, could change everything we think we know about our place in the cosmos.